Hello all, welcome to Chemistry EduHub channel. I'm starting a new series for B.Tech first year students who have chemistry as one of their subjects in the first year. And the very first chapter is water and its treatment. Okay, so water is the basic concept that we are studying from grade 6th onwards, and the range of the concepts that we study are differing. So in this chapter we're going to learn about the water and its treatment. So we know that earth is covered with 75% of water and 25% of land. Now out of this 75% of water, most of the water is salt water and only 1% of it is the fresh water. So though there is 75% of the water, most of the water is not useful for any of the activities. Only 1% fresh water can be used for all the livelihood on the earth and also for all the industrial purposes, for all the activities that we do every day, for drinking, for preparing all the food, etc. So only fresh water is useful. Fresh water is available in rivers, ponds, lakes, glaciers, etc. And the rainwater is the purest water. But this fresh water that is available in the nature cannot be taken directly. It is not potable directly. You cannot drink it directly, because that contains other unwanted materials, because it gets mixed with the minerals present in the ground. Since there will be a lot of minerals in the ground, they get mixed with them and they become they are not potable for drinking. So to make it potable for drinking and other activities, we need to treat it. We need to treat it so that it is useful for our drinking and for doing other activities. So basically, water can be mainly, this potable water is again mainly two types. So soft water and hard water. Okay, soft water is the water that produces lather with soap easily. So whenever you want to test the nature of water, you can wash your hands with water and put some soap in it and see if the lather is heavy or light. So if the soap lather is heavy, such water is considered to be soft water, which is very, very helpful for our daily activities. But if the water doesn't produce any kind of lather or produces very less lather, such water is called hard water. Now this hard water is not potable and it cannot be used for our daily activities. It cannot be used for cooking. It cannot be used in the industries, etc. So we need to treat such hard water by using different methods. That is the meaning of treating of water. Now, soft water is something that produces lather easily with the soap, and hard water is something that doesn't produce lather or produces very less lather. Such water is called hard water. Now, what is soap generally? Soap is a sodium or potassium salt of fatty acids. Soap is formed by the fatty acids. What are fatty acids? They are the long carbon chain compounds with carboxylic acid functional group. So there can be X number of carbons attached to hydrogen, simple hydrocarbon, but at the end we find one carboxylic acid functional group. Such acids are considered to be fatty acids. So here we can use stearic acid, palmitic acid or oleic acid to make the soap. Okay, so there is one functional group, COOH. Now whenever we treat this fatty acids with a strong base like sodium hydroxide or potassium hydroxide, there will be ionization taking place. What is ionization? NaOH can be split into Na plus and OH minus. KOH can be split into K plus and OH minus. And we also know that COOH is a polar molecule or polar functional group. That means COOH also can be split into CO minus and H plus. So whenever we treat an acid with a base, we can see the exchange of ions taking place. Now that results in the formation of the long carbon chain with CO minus ionizes into CO minus anion, and either Na plus or K plus will be the cation. This involves the cleaning process. This is the soap formation. Whatever acid that we take will be resulting into the sodium stearate, sodium palmate, sodium oleate, etc. That is the soap formation. Now whenever we treat this soap with the water, that results in the lather or foam. So that will remove the dirt or the oil particles from the cloth or from the hands or from any surface. This is the soap formation, and the cleaning action involves whenever we use soap with the soft water. Now that will be absent when we use hard water with the soap. So we understood what is the hardness of water. That means the ability to not produce lather with the soap is considered to be the hardness of water. Now what is the reason for the hardness of water? It is the presence of dissolved salts like bicarbonates, chlorides and sulfates. So generally water that is available from the ground can be mixed with the salts of calcium or magnesium. Now what are those salts? Especially the bicarbonates. So bicarbonate is nothing but HCO3 minus ion. So HCO3 minus ion is the bicarbonate. Whenever it gets mixed with calcium or magnesium, it becomes calcium bicarbonate or magnesium bicarbonate. Calcium and magnesium both are di-positive cations, but the bicarbonate is uni-negative anion. And chlorides are also uni-negative Cl minus, and sulfates are di-negative SO4 2 minus anions. So these three types of anions, whenever they mix or combine with calcium or magnesium, they result in the formation of calcium or magnesium bicarbonates, calcium or magnesium chlorides, calcium or magnesium sulfates. Now this results in the formation of hardness of water. Bicarbonates causes the soft hardness. In the hardness also there can be two types, soft hardness or you can say temporary hardness, but chlorides and sulfates cause permanent hardness of water. Temporary hardness can be removed by just boiling of water, but permanent hardness cannot be removed by boiling of water. That needs a proper treatment using some methods that we are going to learn in the further concepts of the chapter. So let us see the reactions here. There is sodium stearate soap. Whenever it is treated with magnesium ion, that is forming magnesium stearate by replacing the sodium ion. Similarly, soap when treated with calcium, it is forming calcium stearate replacing the sodium ions. So soap doesn't produce lather until all this calcium or magnesium ions are removed from the water. Hence the salt should be removed from the water in order to make it soft and potable for the use. Now let us see the cause of hardness. How the hardness is caused in the water. So chemically, water formula is H2O. That means 2 parts of hydrogen combines with 1 part of oxygen. Now the chemical name of water is considered to be hydrogen oxide. It's a binary compound with 2 different elements, and oxygen is the electronegative element with negative charge, so it is hydrogen oxide. The common name is water. So 2 parts of hydrogen combines with 1 part of oxygen by volume. Now what do you mean by volume? Both hydrogen and oxygen are available in the form of gases in the nature. Both are gases. So whenever we have to combine hydrogen and oxygen to form water, this is the balanced equation. So whenever hydrogen and oxygen need to be combined, we cannot take single hydrogen atom or single oxygen atom. This is not possible. We have to take in terms of moles. Mole in the sense, we take 6.023 into 10 power 23 particles of hydrogen, or 6.023 into 10 power 23 particles of oxygen. This is nothing but mole. So as a whole, 1 mole of hydrogen or 1 mole of oxygen will participate in the reaction. Now this 1 mole of hydrogen or 1 mole of oxygen occupies 22.4 liters of volume. Because these are gases, we generally talk in terms of volumes. So that means 2 moles of hydrogen combined with 1 mole of oxygen to form 2 moles of water. Now this water can dissolve many substances in it. Hence it is considered to be the universal solvent because of its polar behavior and high dielectric constant. It can dissolve as many salts as possible. So it is called universal solvent. Water is a universal solvent. Now, what are the dissolved substances that cause the hardness of water? It is the carbonates, chlorides, sulfates of calcium and magnesium. So mainly dolomite or limestone. What is limestone? Limestone is calcium carbonate. Dolomite is calcium carbonate and magnesium carbonate. These two are the main components that are present in the stones in the ground generally. So in the air we find water and carbon dioxide. Water in the form of vapor. When dissolved in the ground, it turns into water. So whenever the water and carbon dioxide get mixed with such carbonates, calcium carbonate or magnesium carbonate, now they turn into calcium bicarbonate and magnesium bicarbonates. Now, as we have already discussed, these two result in the temporary hardness of water. So whenever the water passes through the layers of soil inside in the ground, they dissolve with the salts of calcium, magnesium, potassium and sodium, and they remain as the dissolved salt in the water. That causes the hardness of water. According to the area or the ground minerals that are present in the ground, the dissolved salts may vary, like there can be silica, sand, alumina, manganese, iron. Sometimes in some places there can be fluoride or there can be arsenic, which are not much useful for drinking. So this causes the hardness of water. Now, according to the quantity of salts that are present, the degree of hardness will vary from water to water. Let us see the degree of hardness. Degree of hardness is nothing but, if at all in two places the water available is hard, the degree of hardness may vary from place to place based on the amount of hardness producing salt. Suppose in the two areas the hardness causing salt is calcium carbonate only, but if the amount of calcium carbonate is less in one area, that water is considered to be less hard, and if the calcium carbonate is more, that is considered to be more hard water. So degree of hardness depends upon the amount of hardness producing salt that is present in a given amount of water. So generally, calcium carbonates are the most commonly hardness causing salts that are available in many hard water. So since it is the most common salt, we calculate the degree of hardness in terms of calcium carbonate only. So 100 parts by weight of calcium carbonate can be equated to 136 parts of calcium sulfate, 111 parts of calcium chloride, 164 parts of calcium nitrate, 120 parts of magnesium sulfate, 95 parts of magnesium chloride, 148 parts of magnesium nitrate. That means 100 parts by weight of calcium carbonate hardness is equivalent to these values of other hardness causing salts It's just a comparison of hardness with calcium carbonate and other hardness causing salts. So hardness causing salt in terms of calcium carbonate equivalence can be calculated by using a simple formula. Amount of hardness causing salt by amount in the sense the weight of that salt present in a given amount of water by the molecular weight. That means the according to the formula, whatever weight comes, that is the molecular weight. So let us see, if there is 100 grams of calcium carbonate in the water, what is the molecular weight of calcium carbonate? It is also 100 grams into 100. So this will be 100. GG also gets cancelled. So the degree of hardness is considered to be 100. So that way we calculate the hardness causing salt in terms of calcium carbonate equivalence by using this simple equation. So this is the interrelation between 4 units of hardness of water, that is how ppm is related to milligram per liter, how milligram per liter is in turn related to degree Clark and degree French, etc. So this is a simple relationship that is decoded and given to you. Now let us see the types of hardness of water. So as we've already discussed, hardness can be mainly temporary or permanent. So temporary hardness of water is caused by bicarbonates of calcium and magnesium. So we have already seen the bicarbonate ion is HCO3 minus. So calcium and magnesium, both the ions are di-positive ions, Ca2 plus or Mg2 plus. So by using crisscross method, we can attain the formula. So whenever Ca2 plus combines with HCO3 minus, Ca2 plus or Mg2 plus with HCO3 minus, what we do is we take only the number below 2, and here since it is minus we consider it as 1, and we cross multiply these numbers with the ions. That is nothing but crisscross method. So Ca or Mg, since HCO3 is 2 times, we cannot write HCO3 32, it becomes HCO32. That is not correct. We take in bracket HCO3 twice or MgHCO3 twice. This is the formula for calcium bicarbonate or magnesium bicarbonate, as you can see here. So the reactants are calcium and magnesium bicarbonates that are present in the temporary hard water. Now whenever we boil them, this delta indicates the boiling or simple heating, that the bicarbonates convert into carbonates. Now bicarbonates, when they are present in the water, you cannot see with your eye because they are dissolved. Bicarbonates will dissolve in the water. But when they convert into carbonates, either magnesium carbonate or calcium carbonate, it forms a precipitate, PPT. PPT is not some PowerPoint presentation. PPT is the precipitate. The downward arrow indicates the settling at the bottom. So precipitate is something that will not dissolve in the water. So it comes and collects at the bottom. Suppose if this is your hard water which contains calcium bicarbonate, when heated, upon heating, that gets settles at the bottom. You can see white salt settling at the bottom. Now what we can do when it settles, we can just filter this water off and you can use the soft water which is free from the calcium and magnesium salts. So that results in water and carbon dioxide will evaporate into the air. So this way, temporary hardness that is caused by bicarbonates can be removed by converting them into carbonates which form as a precipitate. This is a simple method for removing the temporary hardness of water. The second type of hardness is the permanent hardness or non-carbonate hardness. That means It is caused by the presence of chlorides, sulfates, nitrates of calcium and magnesium. So chlorides are generally uninegative, sulfates are dinegative, and nitrates are uninegative ions. So when we use the crisscross method like the previous way, the formulas are CaCl2, CaSO4, CaNO3 twice, MgCl2, MgSO4 and MgNO3 twice. So the total hardness of the water can be the sum of temporary hardness and permanent hardness. So whenever we say temporary hardness, there will be only bicarbonates present in them, but when we say total hardness, there can be bicarbonates as well as permanent hardness causing salts also present in it. So total hardness is equal to temporary plus permanent hardness. So we can remove this permanent hardness by using a complexometric method, or we can also say complexometric titration. So for any titration, generally we need an indicator, okay, we need a burette, we need a pipette. So this is a bit complicated. So it's called complexometric method because the EDTA or the ethylene diamine tetraacetic acid that we are using is a complexing agent. That means it forms a complex structure with the calcium or magnesium present in the hard water. So what is EDTA? Ethylene diamine. Ethylene is generally CH2 double bond CH2, but when the pi bond is replaced with two amines, we get CH and this is connected to N. This is generally ethylene diamine, but these two hydrogens are replaced with acetic acids, that is CH2 COOH. CH2COOH, CH2COOH. We change the hydrogen's number according to the valency of any element. Suppose normal acetic acid formula is CH3COOH, but since here carbon is already connected to nitrogen and connected to carboxylic acid, only two hydrogens vacancy is left, so we write CH2 instead of CH3. Similarly, here also you find two acetic acids. This is the ethylene diamine tetraacetic acid formula. So it is EDTA, it's a complexing agent which forms complex with the calcium or magnesium ions present in the hard water. Now this happens at a particular pH, that is 9 to 10 range. So to maintain this pH, we are using a buffer solution. Now what is a buffer solution? Buffer solution is something that when used, it will resist the pH of the solution to some extent. Though the compounds in the mixture are acidic or basic, the pH will not change until a certain range. So to maintain such range, we use generally buffer solutions. So where do we find buffers generally? In our body, blood is a buffer. Okay, so blood will retain the pH of our body even though we eat acidic or basic foods, alkaline foods or acidic foods. Even if we eat, the blood is going to maintain the pH of the body to some extent. So blood is a common or very natural buffer that we see in the body, and we can prepare buffers by using different salts that we see in the coming chapter. And to understand the color change, to understand the titration that it is ended, we use a indicator called eriochrome black tea. Now what is the color of eriochrome black tea? It is generally blue in color. Though the name indicates black, it is blue in color. But whenever it forms a complex with the EDTA, it turns to wine red color. So what is the basic principle of this titration? We take hard water which contains calcium and magnesium salts, and to that what we do? We add areochrome black tea indicator. Indicator is generally added 1 or 2 drops, and buffer solution is also added here, 2 or 3 drops of buffer solution. So areochrome black tea is blue in color, but whenever it gets mixed with the hard water, it turns to wine red color because it forms an unstable complex. Because of the unstable complex formed, it turns to wine red color. Now that is treated with EDTA solution. So then we observe the calcium and magnesium ions will form a complex with EDTA. That results in the blue color again, and it forms the water now is free from the hardness. So this is the basic principle of this titration. Let us see the process of the titration in detail, how the buffer is prepared, how the indicator is prepared and everything, and how they are mixed, and the calculations also let us see. Here's a quick glance of EDTA structure, and when it is replaced with sodium, how it is formed as a disodium salt of EDTA. I've already shown the structure, but have a glance of it. So this is ethylene, 2 amines, but the hydrogens are replaced with acetic acid. This is the basic structure of EDTA, which is a tetradentate ligand. And whenever it is replaced with sodium, it forms disodium salt of EDTA. Now, how it works with the areochrome black tea and all, let us see the format. So hard water contains calcium and magnesium ions. When added with areochrome black tea is blue in color, and the buffer solution we are adding, that results in the formation of wine red color unstable complex. By treating with areochrome black tea, it forms wine red in color. Then when it is further passed with EDTA, it forms a colorless stable complex, and the indicator comes out in the blue color, so that this indicator can be further used in any other reaction. So this is the simple format of removal of permanent hardness of water. So what is the end point here? Whenever the wine red color turns to blue color, we can say that the reaction is done or the titration is done. We can note down the reading. So this is the EDTA complex with metal. EDTA complex with metal. The next part of the chapter is to learn about the potable water. Potable water is the water that we drink, or which is safe to drink is considered to be potable. So the other name for potable water is drinking water. Now, for the water to be potable or drinking water need to meet certain expectations or characteristics. What are those? It should be sparkling clear and odorless. The water that we drink should not smell anything, and it should be crystal clear, and it should be pleasant in taste. It should not taste anything like any other dissolved substances. It should be clean and neat in taste. The turbidity should not exceed 10 ppm. What is this turbidity? The cloudiness. When you look at the water, it should not have any dissolved particles in it. Turbidity indicates the cloudiness or the dissolved particles. It should be less than 10 ppm. Only then it is said to be edible. Otherwise, we need to filter it or do some treatment to the water. And it should be free from any dissolved gases like hydrogen sulfide. Hydrogen sulfide is H2S, which smells like a rotten egg, which is generally not safe for human beings or any livelihood. So the water should be free from such gases. It should be free from harmful chemicals like arsenic, chromium, manganese, etc. These are the D block elements. Arsenic is As, chromium is Cr, manganese is Mn. These are the dissolved salts generally present in the water in very small amount, but still they are very poisonous and harmful to livelihood. Its alkalinity should not be high. Alkalinity is nothing but the pH has to be in the range of 7 to 9, not greater than that. So alkalinity should be medium. It should be reasonably soft. Extremely soft water also you cannot drink. It should have certain dissolved salts and minerals in it, and that will be the characteristic of our potable water. And it should be free from any microorganism causing diseases causing microorganisms. So generally through water lot of diseases will be transferring from one person to the other. So water is the main source of all diseases. So the water that we drink should be very clean and free from all the microorganisms. It should be free from dissolved gases like carbon dioxide. Generally, water dissolves oxygen and carbon dioxide, but compared to oxygen, carbon dioxide gets dissolved in larger quantity in the water compared to oxygen. So, carbon dioxide dissolved water is not safe for drinking. And the total dissolved salts, we generally say it as TDS of water. The TDS of water should not exceed 500, should be less than 500 ppm, but generally the suitable TDS for drinking water is between 100 to 200 ppm only. Above that, the water that we drink should be treated with some chemical treatment or some boiling can be done. So these are the characteristics of potable water that we drink every day. The water that we get every day to our houses, it is generally the natural water that is obtained from rivers and canals, but we cannot get it directly from the canals or rivers individually. So what does the government do? It makes sure that everybody gets the drinking water which is free from all the unwanted materials, and government, municipal corporation takes the necessary steps in order to remove all the impurities by passing the water through various treatment processes. So let us see the processes that are involved in the treatment of this municipal water in various steps. The very first step and the basic step is to remove the suspended impurities. Suspended impurities is which are present in the water, which are tiny particles and heavy particles as well. So the first step in the removal of suspended impurities is the screening. Screening is nothing but the raw water that is obtained from the canal or the reservoir is passed through screens having large number of holes. Maybe the water is passed through something of this type, where the heavy floating objects, rags and sacks, etc., they can be separated or filtered by the screening method. This is the first and foremost basic step that is involved in the removal of suspended particles. Once the screening is done, once the floating matter is removed from the water, the second step is the sedimentation. Now, sedimentation and coagulation, these are the two processes that are involved based on the size of the impurities present in the water. Suppose if the particle size is large enough, then we use sedimentation. If the size of the particles is very small, like in the case of colloids, the particles are small but do not dissolve. In such case, we use coagulation process. These are all the processes that you learn in 6th class, and it is implemented again in these methods. So the process of allowing the water to stand undisturbed. Suppose if you take a glass of water and add some fine mud particles in it. So what you see when you stir it, the whole water turns into mud water. But if you keep it aside without disturbing for some time, then we see all the mud particles get settled at the bottom, and you can see the clear water on top. This is the mud, and the clear water can be seen on the top. This process is called sedimentation. Now, how can you separate it? You can just filter it or directly pour off the upper layer of water where the bottom layer is just the mud or the sediment remaining. So this is a simple method where we use the technique called gravity. Because of the earth's gravity, the heavier particles get settled at the bottom and the lighter particles move to the top. So this is a sedimentation process where suspended matters settle at the bottom and the water remain in the upper layer. Now this is just a sedimentation process when the suspended particles are large enough. But when the water contains fine clay particles or the colloidal matter is nothing but the particle size is not very small, not very large. It is in between and does not dissolve in the water like the milk particles. Okay, so then it is necessary to follow the coagulation technique after the sedimentation process also. So what is coagulation? We add certain coagulants. Now what are these coagulants? They can be alum or ferrous sulfate. Alum is nothing but the aluminium potassium hydrated salts. In Telugu we call it patika. Okay, alum or ferrous salts where aluminium and iron ions, tri-positive ions, are present in them. Now those chemicals are treated with the water. They form insoluble gelatinous flocculent PPT. Insoluble gelatinous in the sense it forms like a gel. All the clay or the colloidal matter that is present, they stick to the coagulants and they form a thick precipitate kind of material which comes down or descends through the water and forms a big flocks so that they can be easily settled down and removed from the water. This process is called coagulation, where coagulants like alum or ferrous sulfate are used, and colloids generally have charges, positive or negative. So what these coagulants do, they neutralize the charge of the colloidal matter. That results in the formation of large lumps of clay particles or bigger flocculent particles that can be easily separated from the water because they settle at the bottom due to gravity. This is a method called coagulation followed by sedimentation. This is employed only when the particles when the water contains clay or colloidal matter in it. Otherwise we can just go with the sedimentation process. Now what is the reaction happening here? When you take alum, the main ingredient or the chemical is the aluminium sulfate treated with calcium bicarbonate. Then it forms aluminium hydroxide. These are the precipitates that gets settled at the bottom. So this forms the flock and gets sedimented. Then similarly, sodium aluminate treated with water also forms aluminium hydroxide, which forms a gelatinous PPT so that can be filtered easily. The third step in the first process is the filtration. So the first is we use screening. Then second is the sedimentation followed by coagulation. Then the third is filtration. So these are the steps that are involved in the removal of the fine and small particles. Now what is filtration? Once the small particles got coagulated or sedimented, now they need to be filtered. That is the last step in the first last method in the first step. Okay, so what is it? Process of removal of colloidal matter and most of the bacteria or microbes by passing through a fine sand. So generally when you go to any water bodies, the stagnant water will be more contaminated compared to the running water, because running water will have lot of stones in it or sand particles in it or gravels in it. So what will happen when the water passes through these stones and gravel and sand? It will filter or removes off all the unwanted materials. The water gets filtered and water becomes very, very neat and clean. So the same technique is used here also. So the bed of fine sand and also the granular particles. Fine sand is something which is very soft. Granular sand is something which is a bit higher, larger sized particles compared to the fine sand. Then the sand filters are used in order to remove all the sedimentation and coagulation that happened in the second step. So this sand filter also will be of 3 layers. Again, ultrafiltration is happening here. What is it? Fine sand, then the coarse sand layer and the gravels. So sand can be very soft. When you go to beaches, you will find very soft sand, that is fine sand. Coarse sand is which has a bit rough sand, and the gravels are small stones like pebbles, which also removes the coagulation happening in the water. Now for this sand filters, for the sand beds, there's an inlet and an outlet. So inlet is to pass the impure water, and outlet or the exit is to collect the pure or filtered form of water. Now once the water is free from all the impurities and the sediments and coagulants, the second step is to remove the microbes. So though we pass it through many filters and coagulants etc., that will not kill the microorganisms present in the water. So these microorganisms can cause a lot of diseases when we take it directly. So the water is not after the first step also, it is not still potable. It still contains the microbes. So we should get rid of these microbes by either disinfection or sterilization processes. So disinfectants are those which are when the water is treated with the chemicals that can kill the bacteria. So the substances that have the ability to kill the bacteria are called disinfectants. This is a chemical treatment. The second is the sterilization, which is simple. That is, when the water is being boiled, then the microorganisms get killed because of the heat, because they cannot sustain that hotness. So such water is considered to be, such process is the sterilization process. So for the disinfectant step, we can either use ozonization or chlorination. Chlorination is the treatment with chlorine and ozonization is the treatment with ozone. So among these two steps, chlorination is the cheapest and most affordable method, and ozonization is the expensive method, but it is also equally useful. Now what is ozonization? When the water is passed into ozone, then the water gets ozonized. What is actually happening? Ozone is nothing but O3. This is exactly the same ozone that protects the earth from harmful rays that is obtained from the sun. So O3 is highly unstable. So whenever there is ozone, it immediately converts into molecular oxygen and forms the nascent oxygen. Nascent oxygen is nothing but newly formed or newly born oxygen, which is in the atomic form. Simple O, which is formed when the ozone splits, is called nascent oxygen. So this nascent oxygen is a very powerful disinfectant because it treats the bacteria and oxidizes the organic matter. Then the water becomes free from microorganisms by killing the bacteria. So nascent oxygen treated with microorganisms kills them. So this is the ozonization method. This allows the water that is ozonized can be directly sent into sterilization tank, and the water can be ready to drink because it's simple oxygen and not harmful to any livelihood. So what is the advantage? It removes all the color, odor and taste without forming any kind of residue. But the only problem with the ozonization is that it is expensive, because dealing with nascent oxygen or atomic oxygen is highly risky, highly difficult, because it is a atomic oxygen and highly unstable. To maintain all that conditions for the nascent oxygen to be formed is highly difficult. It needs a lot of equipment and expenses to clean that water. So ozonization is not generally performed by any persons except for the laboratory purposes. The second and the most affordable process to treat the microbes present in the water is the chlorination process. So this chlorination is nothing but process of using chlorine as a powerful disinfectant. So whenever you go to any swimming pool, generally you get the smell of chlorine. It's because of the bleaching powder that they use in order to sterilize the water or remove the unwanted materials, because many people use it so it gets dirty. So in order to remove all the germs causing diseases, they generally use the bleaching powder. So we can use the chlorination by using 3 different chemicals. One is chloramines, the second is bleaching powder, the third is the chlorine directly as either a gas or some concentrated solution. So the first process is by using or by passing chloramines. Now what are chloramines? Cl2 is chlorine. When one of the chlorine atoms is replaced with amine by treating with ammonia, you get chloramine, that is ClNH2. So chlorine treated with ammonia will form chloramine by forming hydrochloric acid as the byproduct. So generally we take 2 times of chlorine mixed with 1 time ammonia in the 2:1 volume ratio. So this generates the stable chloramines. Now what does this chloramines do when treated with water? They form hypochlorous acid. Now this is your powerful disinfectant to remove all the microorganisms. So what is the function of hypochlorous acid? It inactivates the enzymes. So generally, for any process to take place in the nature, enzymes are very much important. So if the enzymes are stopped, enzymes function is stopped, then the process automatically gets slowed down and ultimately it stops. So HOCl or hypochlorous acid will inactivate the enzymes present in the bacteria and kills them. So chloramine is the useful disinfectant that we use in the swimming pool. Also bleaching powder also can be used in the swimming pools. Then the second one is by using bleaching powder. The formula of bleaching powder is calcium oxychloride, CaOCl2. So CaOCl2 generally breaks down in the water as COH twice and Cl2. Now this Cl2 will be your disinfectant. So that when treated with water forms again hypochlorous acid, which acts as a disinfectant to remove all the microbes. So these are the simple methods where the chemicals are also cheap and can also work effectively. The third is the process of applying chlorine. Directly it can be taken as a gas, or we can mix it with the water to form some solution. So chlorine when passed into the water, chlorine gas when passed through the water, it forms hypochlorous acid. If you can observe, in the 3 steps, the final product that is obtained is hypochlorous acid only. So that will kill the microorganisms present in the water. So if at all excess amount of Cl2 is added to the water, it kills the bacteria and also removes the organic impurities. And the excess amount will be leaving the chlorine with bad taste, odor and toxic effect in the water. So we cannot just add any amount of chlorine to water. That also needs some calculation according to the amount of water that is to water body to which we are adding. So amount of chlorine that you add to kill the bacteria is nothing but break point of chlorination. Only such amount is required to treat the water. If you use less, the microbes will not go completely. If you use more than that, then the water will be toxic. If accidentally if you drink or smell it or taste it, it's going to be harmful anyways. So we need to use a limited or the required amount of chlorine to treat the water. Let us see this in the graphical manner. This is a graphical representation to talk about the chlorine dosage. So when the required amount, in the first case the chlorine oxidizes the water, impurities present in the water. Second case, the chlorine that is remaining will react and forms the chloramines and other chloroorganic compounds, and this is the break point where it kills the microorganisms and forms hypochlorous acid. This is the required amount. If at all excess chlorine or free chlorine is available, that can cause a residual chlorine in the water and will be the cause of all unwanted reactions in the water. So the advantages of this method is it removes the taste of the water, it makes the water colorless, ammonia oxidizes the organic matter, and it destroys all the bacteria and pathogens. It prevents the weeds growth. Weeds are nothing but the unwanted plankton present in the water. And what are the disadvantages? If at all it is over-chlorinated, that can lead to bad taste and smell, and over-chlorination can be removed by passing through carbon by the addition of, and also by the addition of sulfur dioxide and sodium metasulfate. So these are the methods. If at all the water is accidentally over-chlorinated, that can be treated with sulfur dioxide and sodium metasulfate, and which can be removed as precipitates or dissolved salts, and the water will be free from over-chlorination. So these are the steps that are involved in the removal of unwanted impurities. So if we see the flow chart of the water treatment, then that goes this way. So water or the municipal water is treated with the first step, that is the screening by removing the large particles. Then it is passed through sedimentation. Then it is passed through filtration, and if at all the particles also contains colloidal particles, then it is passed through coagulation as well. So sedimentation, coagulation goes side by side, then the filtration. Then once the water is free from all the impurities, then it is passed through disinfection or sterilization by using either ozonation or chlorination. Then we get the potable water. These are the various steps that are involved in the removal of impurities and making the water potable by the municipal corporation. So these are the steps.